Hi, welcome to the Laplace Transform lecture. This will be the first part that we are going to cover. I've tried to list here the topics that we are going to see. First one is definition of Laplace transform, and then I will introduce you with two singularity functions, the step function and the Dirac delta function, along with the shifting property. And then we will try to derive some Laplace transforms for important functions like a constant. It's like a DC voltage, for example, with constant magnitude. A ramp function, t at u at t. U at t is basically meant to limit the function from 0 to the positive part of the time domain. Exponential function and the trig functions like sine and cosine omega. And then we'll try to cover inverse Laplace transform. We'll see how we can extract the time domain from an S domain, and then we have a list of important properties of Laplace transform. Then we'll see the initial and final values theorem. So let's see the first part, which is a definition. So when we try to define Laplace transform, we have a time function f at t, which will be converted into a frequency domain f at s using the Laplace transform. So the Laplace transform of any function f at t is defined as the integral from 0 to infinity of the function f at t with respect to e raised to minus st dt. So this gives us the definition. So whenever we have any function as a time function, then if we multiply that by e raised to minus st and integrate that over 0 to infinity as improper definite integral, that would give us a function in S domain because the t domain has already been integrated. So bearing this in mind, if that's the definition to transform a function from time domain to frequency domain, then the inverse, which is represented as inverse Laplace transform of f at s, it can be done using excuse me, two methods. First, as we are going to see here in inverse Laplace transform, we are going to use some method of residue techniques to convert it into the basic functions. Otherwise, we can use a simple integration method, which is 1 over 2 pi j, and we are going to integrate it from sigma minus j omega to sigma plus j omega, and we are going to integrate the function f at s with respect to I will move that one a little bit. Alright, so we are going to integrate. Let me write that here. Okay, that is going to be 1 over 2 pi j integration from minus j infinity into plus j infinity of the function f at s e raised to st ds. But we are not going to use that. That looks a bit complicated. We will have some other much easier ways to do the integration or the transformation to Laplace transform. So that will be the definition for Laplace transform. So we are done with that. Alright, let's see some Laplace transforms. Before that, we are going to see, as we have seen it on our last class, we have two functions which are singularity function. So a function is said to have a singularity function if it's not integral, if it does not have an integration for a certain time function, and if the limit doesn't exist as time is approaching to infinity. So if it is not integrable for a certain interval, it might be till infinity. If it is not integrable for t till it reaches infinity between some function t1, and if it doesn't have the limit of the function, for example it might be f at t, if it doesn't have this as t is approaching infinity, then it is called a singular function. And the two most important singular functions that we have been talking about are u at t, which is our step function, and the Dirac delta, which is our impulse function. So if we start with the Laplace transform of the u at t and Dirac at t, then u at t is, well, don't complete that. So u at t, which is our Dirac function, is originally defined as a function which has got a value of 1 for t greater than 0, and it has a value of 0 for t less than 0. So if I put it on a curve, it will have 0 till it reaches 0 on the x-axis, and then after that it will have 1 for all values of t greater than 0. So if we take the Laplace transform of this function u at t, then according to our definition, it will be the Laplace transform of u at t is going to be the integration from 0 to infinity of u at t e raised to minus st dt, right? In which case, u at t, as we have seen already, has a value of 1 for anything greater than 0. So this integration is simply, it is minus e raised to st dt from 0 to infinity. So that when we integrate e raised to minus st, it should give us minus 1 over s, which is for this guy here, multiplied by e raised to minus st, which is defined for the improper integral from 0 to infinity. So that gives us, for a value of infinity, if we substitute that infinity to this t part, it will give us 0. So the value in here is going to be 0 minus, when we give 0, or when we put 0 in here, so the whole value will be e raised to 0, which is 1. So we have that value. And when we multiply this thing, it should give us 1 over s. So that tells us that the Laplace transform of u at t is always 1 over s. So if the Laplace transform of u at t is 1 over s, then that also gives us the Laplace transform of any constant. For example, if we have a DC voltage of value, say 6 volt, then in order to transform this using Laplace transform, that 6 volt is basically, it can be transformed into plus minus 6 u at t, right? As long as the voltage starts at t is equal to 0. So when we transform that using Laplace, the Laplace transform of a 6 u at t is going to be 6 times the Laplace transform of u at t, which gives us 6 times the Laplace transform of u at t is 1 over s. So that gives me 6 over s. Therefore, the Laplace transform of any constant k, so the Laplace transform of a constant k is, as long as it starts at 0, can be defined as the Laplace transform of k times u at t, right? That gives us k over s. So that is the Laplace transform for a t function. Alright. So when we have a unit step function, which is a constant function as you have seen here, then the Laplace transform is always going to be 1 over s. That's a good point we have to remember. So this will be one of our important transform function. Unit step function is transformed into 1 over s in the s domain.